Okay, rotating coordinate systems number 5. This is one of those problems where you have to do it with the origin fixed at 2 different places. And I think this is a really useful way to make sense out of this stuff that I know is tricky to make sense out of. So what we have is a disk like this that's rotating about a vertical axis. And then on this side, we have a hinge that's rotating about an axis that's into or out of the page. The horse is the disk, and the rider is the, whatever that is, that other member. And you can see that because the axis of rotation of the disk doesn't change as the rider moves, but the axis of rotation of the rider does change as the horse moves. Okay, so if this disk is rotated another pi over 2 radians, then the axis of rotation of the arm is moved by 90 degrees, moved by pi over 2 radians. Okay, so that means that for both of these 2 parts, and the 2 parts are so actually the harder one is the one with the coordinate system here, and I guess that's what it says to do as part A. It doesn't matter which order you do these in, but okay, so I'm going to set this one aside. I'm going to do this one second, because first I'm going to do the one that would be the more natural choice, that if you weren't told to use that coordinate system, that first one I drew, there's not really any reason to do it, but except to make sense out of this problem. Okay, so I'm going to do the one at the center first, and I'm going to do the one at the hinge second. And the reason for that is, notice that if our coordinate system is at the center of the disk, even though that coordinate system is rotating with the disk, the origin isn't moving around. The origin is fixed. There's no acceleration of that origin. And so we don't have to use relative motion for that. For that second one, the axes are changing orientation. That coordinate system is rotating. And in addition to that, the origin of that coordinate system is in circular motion. So it's also accelerating, and that means we'll have to use relative motion. Okay, so that'll be a pain. All right, so first I'm going to use a coordinate system that's fixed on the center of the disk, okay? It's moving with the disk, so it is rotating. And so we're going to use, we're trying to calculate in both cases the acceleration of this point here. I'll call it P. Okay, so the acceleration of that point P is going to be the acceleration of that point P that's observed in that rotating coordinate system, plus capital omega dot crossed with P, plus 2 times capital omega crossed with the velocity of that point P that's observed in the coordinate system, plus capital omega crossed with the quantity capital omega cross P. And that's all we have to do. We don't have to use relative motion. So let's just figure out what the pieces are for this. Okay, so what does it look like is going on so you can think of this as, forget about the motion of the horse for now. Imagine that that the disk is not rotating. What does it look like? What does the motion look like for that point P to us as an observer? And what it looks like is just circular motion. So this is going to be the watermelon equation. Okay. Then we have to calculate P. What does the velocity over here look like? Again, if we forget about the rotation of the disk, we stop that temporarily. All we see is a circular motion of P, like about an axis parallel to Z. And so this would be, our lowercase omega crossed with an R vector. Okay. Well, let's figure out what some of these things are. First, the P vector, the position vector, in our coordinate system. And remember, our coordinate system that we're doing here is at the center of the disk. So the P vector is just the vector that goes from the origin to the point P. The radius of the disk is 1.5 meters, so it's 1.5 in the negative x, and then 1.3 in the positive y. Okay. The angular velocity of the coordinate system. Well, it says that this disk has an angular velocity of -5 radians per second. That's about the y-axis. So this is going to be 0, -5, 0. And it says that the angular acceleration is +10 of that disk. So capital omega dot is 0, 10, 0. And now we have to think about the stuff that we need for the rotating coordinate system. So now we're forgetting about the motion of the disk, and we're just thinking about the observed circular motion of P around its hinge. It says that at this instant, it's rotating about its hinge with a constant angular velocity of 8 radians per second. The axis of rotation is the z-axis. This circular motion of this arm is in the xy plane. So lowercase omega, this is the omega just for that point as observed in our coordinate system, is 0, 8, 0. And it says it's constant, so alpha is 0. And now the r vector. Now you have to think carefully about the difference between the r vector and the p vector. Our p vector was this one. It goes from the origin of the coordinate system to the point you care about. For circular motion, the circular motion of P around that hinge, all we care about for R is the vector from the center of the circular motion to the point that we care about. So in this case, that's only going to be 0, 1.3, 0. Okay. Now it's just a matter of filling this stuff in. So the velocity of P observed is 0, 8, 0, crossed with the r vector, 0, 1.3, 0. Since those are parallel to each other, that's a 0 vector. The observed acceleration of P is alpha cross r plus 0, 8, 0 crossed with the quantity 0, 8, 0 crossed with the r vector. Oh, no, I'm sorry. The mistake that I made is my angular velocity of the body, of the arm, is not parallel to the y. It's not rotating about the y-axis. That would be like spinning about its long axis. In this coordinate system, forgetting about the motion of the disk for a second, that arm is rotating about the z-axis. So this should have been 0, 0, 8. So that changes all this stuff a little. Okay, so this is 0, 0, 8. And get a different answer for this. So I think that should be 10.4 negative. There's no alpha, so this goes away. These 8s should both be in the z-axis. Okay, so this is negative 10.400, and we're crossing it with 0, 0, 8. And so those together come out to be 83.2 negative. This one is 0, and so our answer for this whole thing comes out to be 0, negative 83.2. 0. That's the observed acceleration of p. What a camera that's fixed to that rotating disk would think is the acceleration of p. Okay, and so we have observed velocity, observed acceleration. We still need, well, now we can just start filling this stuff in, I think. So A sub p is equal to 0, negative 83.20, plus this second term, which is 0, 10, 0, crossed with the p vector, which was negative 1.5, positive 1.30, and then plus 2 times the angular velocity of the coordinate system, 0, negative 5, 0, crossed with the observed velocity vector, which is negative 10.400, plus 0 angular velocity of the coordinate system, 0, negative 5, 0, crossed with the quantity 0, negative 5, 0, crossed with the p vector, and I'll be right back with you and we'll get the answer. Okay, so what we get for a final answer for the acceleration of p is 37.5 for x, negative 83.2 for y, and negative 89 for z. These are all SI units, so this is meters per second squared. All right, so that's the answer using the simpler probably of the two coordinate systems. But now we have to do the same thing, and these answers have to match if you do it right. We're going to do the calculation where the origin is moved over to the base of that arm, moved over to the hinge. Okay, so now the coordinate system origin is at the base of the hinge. Okay, well, the coordinate system is still rotating with the horse, with the disc. So we're still going to have to use rotating coordinate systems. But notice now that origin is also accelerating because it's in circular motion around the center of the disc. So we can think of this as, let's name some of these points. Let's call this point C, the center of the disc, okay? And I'm going to call this the origin, O. And then we have P. Okay, so now the acceleration of P relative to the ground, or relative to the, relative to, this would be C. You know, C is fixed to the ground, it's not moving, is equal to the acceleration of P relative to the origin plus the acceleration of the origin relative to C. Okay, this is going to be the rotating coordinate system equation. And this is just simply going to be circular motion of the origin of our coordinate system about C. Well, let's do that first. So long ago, many months ago, we had already done problems where we could calculate like the acceleration of this point O in circular motion around C. So let's do that first. So the acceleration of the origin around C is the watermelon equation, alpha cross R plus omega cross quantity omega cross R. The body that's rotation we're looking at right now is the disk. And so alpha is the angular acceleration of the disk, which is 0, 10, 0. Omega for the disk is 0, negative 5, 0. That's given. And the R vector is from the center of the circular motion. So all we're doing right now is calculating the acceleration of O. So the R that we care about is from the center of the disk to O. So that R vector is negative 1.500. Okay. So the acceleration of O relative to C is 0, 10, 0 crossed with negative 1.500 plus 0, negative 50 cross quantity 0, -5, 0, cross -1.5, 0, 0. All right, well, this one comes out to be 0, 0, +15. This one is 0, 0, -7.5, and we're crossing that with 0, -5, 0. So together these come out to be 37.5, 0, 0. And so altogether, the acceleration of the origin relative to the center of the disk is 37.5, 0, 15. Okay, well, now that we're done with that, we can just go about calculating the acceleration of p relative to the origin as if that origin wasn't accelerating. We'll just add that on at the end now, according to relative motion. Okay, so now we're calculating the acceleration of p relative to the origin. And this is just using a rotating coordinate system. So we know that this is equal to the observed acceleration of p plus the acceleration dot of the rotating coordinate system crossed with p plus 2 times the angular velocity of the rotating coordinate system crossed with the observed velocity of p plus capital omega cross quantity capital omega cross p. Okay, well, again, this is going to be watermelon. This observed velocity is going to be omega, not of the coordinate system, but of the arm, crossed with r. So let's calculate those. So a sub p observed is the angular acceleration of the arm as observed in the rotating coordinate system, as observed by a camera that's stuck to the disk, crossed with r, plus lowercase omega cross quantity lowercase omega cross r. The arm does not have any angular acceleration, so this term goes away. Omega for the arm is, we wrote it way up here somewhere, omega for the arm is 0.008. And now r, we have to be really careful with these p's and r's. We've moved the coordinate system now. we've moved the origin of the coordinate system. That isn't going to change the r vectors for the circular motion, but it is going to change the p vectors, because p goes from the center of the circular motion to the point that you care about. But r is still going, if we look at the picture, our r vector is still the vector from the center of the circular motion at the origin to p. So for this part of the problem, p and r, the definitions are the same, but you always should remind yourself, what's the definition of the vector that I'm looking for? Okay, so omega is, we already did omega. R is 0, 1.30. And so this comes out to be 0.008 crossed with what you get from these two, which is negative 10.400. And cross those, and you get 0, negative 83.20. Now let's calculate the observed velocity. That's just 0.008 crossed with the r vector. And so that is negative 10.400. Now what about the other stuff that we need? The angular velocity of the coordinate system and angular acceleration of the coordinate system. Those aren't affected by moving the origin. That's just talking about how quickly the orientation of the body is changing. Okay, so it doesn't matter where you're looking at that from. It's changing orientation at the same rate. So this is going to be zero, negative 5, 0. Angular acceleration of the coordinate system is 0, positive 10, 0. And p, so remember the definition of p is a vector from the origin of your coordinate system to the object that you care about. In this case, that's going to be the same as our r vector was a minute ago. That's just going to be 0, 1.30. Okay, let's put it all together. So we're going to this big rotating coordinate system equation. So the acceleration of p relative to the origin is 0, negative 5, 0, crossed with 0, wait, what am I doing? No, so first I'm going to go, it's equal to the observed acceleration of p in the coordinate system. That's the thing we calculated. So that's 0, negative 83.20. And then plus omega dot of the coordinate system crossed with p. Notice that those two vectors are parallel, and a cross product of parallel vectors is always 0, so this one goes away. Plus 2 times omega for the coordinate system crossed with the observed velocity of p which we calculated as negative 10.400, plus omega of the coordinate system crossed with the quantity omega of the coordinate system crossed with the p vector and this whole thing comes out to be 0, 0, negative 104. These two together notice that in the parentheses we have the cross product of two parallel vectors, so that goes away, so this whole thing goes away. And what we get is the acceleration of p relative to O is equal to 0 for the x component, negative 83.2 for the y component, and negative 104 for the z component. But remember, we have to use relative motion for this one. So our final answer of the acceleration of p relative to the ground, or the way I have it written is p relative to the center of that disk, which is fixed to the ground, is equal to the acceleration of p relative to the origin plus the acceleration of the origin relative to the ground, which was the first thing we calculated here, acceleration of the origin relative to c is 37.5015. And if you add those two together, you get 37.5, negative 83.2, negative 89 meters per second squared. That needs to match our answer from the first part. So let's look back farther. Positive 37.5, negative 83.2, negative 89. So it works out perfectly. It's, it's tricky, but doing problems like this, trying to move the coordinate system and see what that changes and making sure that you get the right answer is a great way to make sure that you understand these ideas.